welcome back. So we'll continue the lecture in which we were discussing about the measurements. So we discussed about the measurement classification recently and the theory of measurement accuracy, how the theory is being developed, how do we do the calculations. So what are the various ways that the propagation of the calculations goes. So it goes like this, as we discussed: true value, conventional true value is obtained, the measurement results have some errors. Those errors are used to have interdeterminacy or to obtain some inference. So there is an interdeterminacy of measurement results based upon errors, which gives us some interpretation about the results, that to what extent are our results correct. So next is valid measurement. It is very important that the measurement is valid. So this can be compared with the accuracy and precision, like has been discussed by Dr. Ram Kumar before. The data or the readings or the observations that we have gained or that we have obtained are to be valid to work on them. See, there are two major kinds of errors. We will discuss upon that as well: systematic errors and random errors. I will just discuss before that what is a valid measurement. You can see in this matrix there are 4 measurements. The perfect result should have been when it hits exactly at the center. This is the perfect result, exactly at the center. I am at quadrant number 4. In the first quadrant, you can see this is the quadrant number 1, 2, 3 and 4. In the first quadrant, you can see the results are all scattered. So it is not reliable. Whatever the instrument we are using or whatever the observations we have taken, those are not reliable because those are very randomly scattered. So it is a scatter which is random, but it is within our acceptable, it is within this target board. So that is why this is valid. Okay. So in quadrant number 2, it is unreliable and unvalid. See, the thing is that, you know, if I take average of all these dots, all these values, if I take distances from the center, let me say distances, this distance is A, B, C, D, so on. If I take average of these distances or the distance from the center, okay, the final result would be here. This is average. Average, or in statistical terms we call it a mean, the distance from center. So what would happen? You know what would happen if I take it as a positive direction, this as negative direction, and so on from here to positive and negative. You know, this distance, let me say this point would cancel almost this point. Okay, this point would cancel this point approximately. So overall that average would be, if I take positive negative, the average mean would be 0. 0 means exactly at center. That is why this data is, this kind of information is somewhat valid. However, in this it is not reliable. In part 2, in quadrant 2, it is not reliable, not valid. But in this part, quadrant number 3, it is reliable because the data is too close, and in quadrant number 4, it is both reliable and valid. It is at the center and also all the observations are closed. Now, if I talk about precision and accuracy, you can very well determine or very well look into this. Based upon that, this is accurate, this is precise, accurate and precise actually. This is precise and not accurate. So this is not precise, but this is accurate. So, this is the actual definition. Accuracy means, when we talk about accuracy, we need to see the overall data, what is the mean. If the scatter is there, we can work on that. So, this is the kind of a random error. We are working on the random errors. The statistics, whatever we will work on the random errors, not a systematic error. This is in quadrant number 3, the kind of error that is there is a systematic error. Systematic error, whatever the values are, they are all on the right hand side. If someone is targeting this thing, it has to just come below 45 degree towards the left and it will come to the center. So, this distance is our bias. But here we cannot work much in quadrant number 2. Okay, this is neither accurate nor precise. Okay, so the data has to be valid. Next is another measurement method I could have put in the various classification of measurements. This measurement is linear versus stable, or linear is not versus, linear and stable are two different kinds of measurements. Linear measurement method is the measurement method of system is called linear if it has no bias, or if its bias is constant in the measurand. Next is stable. A measurement method of system is called stable if both its precision and its bias for any measurand are constant across time. Across time it is constant. So, linear and stable. Could you please see which is the linear measurement here? Just see the definition again. It has no bias, or if it is, its bias is constant in the measurand. So, I think this is linear and this is linear. Here it has no bias, here the bias is constant. So, mostly we will be working on this kind of data, the data which is unreliable but valid. So, this kind of data is obtained, that is in quadrant 1 mostly, and we work on this to bring some statistical inference. Next is uncertainty. Uncertainty is equivalent to or similar to the errors. When we talk about errors in measurements, those are in statistics we call it uncertainty, or we can also call it errors. I can use this interchangeably here. However, there is the difference between errors and uncertainties. Sometimes errors is the term that is also used for the mistakes that are made. But in this context, in the specific module in which we are working, when we will talk about errors, the errors are not mistakes. Errors is just the uncertainty, that the results are not certain, and we just need to see what is the reason for that, or could we correct that somehow. We will try to see that. So, uncertainty, it is the estimate of the error. The estimate of the error is known as uncertainty. So, it includes both bias and precision errors. We need to identify all the potential significant errors for the instruments, all the potential significant errors. The word significant is being used again and again here. I am also saying the word. What is significant? Significant, literal meaning of significant is it having some influence? Is it having some effect? Is it bringing some change? Actually, is it significant or not? If the errors are significant, we need to work on that. If the errors are not significant, we might ignore that. Or there might be some errors which are not due to the instruments. Those are called noise. We have discussed that. We have signal to noise ratio, all those things. Those are the external factor, the environmental factors that we cannot control. The factors which we can control within our environment, within our experimental setup, those are the sound factors, sound to noise ratio is taken, those are the factors, those are the errors which we will work on. So, uncertainty is the estimate of the error, and it is to be identified for all the potential significant errors for the instruments. All the measurements should be given in three parts. Number 1, mean value. Number 2, uncertainty. Number 3, the confidence interval on which this uncertainty is based. We will discuss about significance and confidence intervals. So, in statistics there are certain assumptions. So, here 95% confidence interval means the significance level is 100 minus 100% actually minus 5% is equal to 100 minus 95% is equal to 5%. This is significance level. So, the broader meaning, the exact meaning we will discuss when I will discuss the probability distribution and specifically normal distribution. I will talk about the confidence intervals, significance levels, and other parameters or other statistics that are important. So, broadly, confidence interval is the confidence or the assurance that whatever we are telling, that this is the mean and this is our uncertainty, we are telling this with 95% confidence. 100% confidence is never there. This is the characteristic of uncertainty, or this is the characteristic of statistics as well, that we have certain confidence level. In mechanical measurements, 99% confidence level could also be there, and in certain maybe micro manufacturing or nano manufacturing, sometimes the confidence intervals are much greater. It is 99.997, those are known as Six Sigma, we will discuss those. So, we have to tell that what is our confidence interval in which we are working overall. So, if you are 95% confidence, if you are 95% confident, what is the inference? If you are 90% confident, what is the inference? If you are 99%, what is the inference? So, what we can say, sometimes it happens that it is significant at 90%, but not 99%. 90% confidence interval, we are 90% confident that the data is significant. At 99% it cannot be. We will discuss this when we will draw the normal curve. So, uncertainty has certain characteristics. It can be given in absolute terms or relative terms. So, it can be expressed in both the ways. Absolute terms means uncertainty is actually the mean value plus something that we add to mean value, add or subtract to mean value is uncertainty. So, this uncertainty, for instance, if my value, so for instance the height, if I calculate the height of some instrument, let me say height of this pen, okay, this is about 150 mm, okay, this is actually a stylus, so this is about 150 mm. So, it can be plus minus something, it is, let me say 150 mm plus or minus 0.5 mm. So, this is the mean value, this is our uncertainty, I put epsilon. In relative terms, what could be relative terms? Relatively, it could be I could pick percentage here. So it can be 150 mm plus minus. So what is 0.5 of 150? So this is actually delta L by L, that is length is this is error by this. Here I am actually calculating delta L by L into 100, this is percentage delta L, here is 0.5 by 150 into 100, this comes down to 50 by 150, and across this is equal to 0.33, okay, plus minus 0.33%. So you can see in absolute terms the uncertainty is in the same units, in relative terms it is percentage, or it might be some other quantile or quartile of this, something like that, okay. So types of error, just to recall the two major types of error, systematic error and random error. In systematic errors, same error value by using an instrument the same way, same error value comes, like this was the bias which I just showed, this is a systematic error, okay, and this is a random error. So here we are telling it is same error value by using an instrument in the same way, provided the thing is that if it is provided that all other conditions remain same, the instrument is the same, maybe the experimenter is the same, and the environmental conditions are same. So it is, if the error value, here the error value is same, okay. So error value is same, whatever the error value is, for instance 5 volt has to be final true value. If results are 5.1, 5.1, 5.1, 5.12, 11, so on. So this is a systematic error, okay. Random error, it may vary from observation to observation, full stop, perhaps due to inability to perform measurements in exactly the same way every time. This error might be due to the change in environment, due to the change in instrument, due to the change in the condition, the experimental conditions, due to the change in experimenter. There might be any change, but the thing is that the error is random, it is scattered. So it is something like that, it is something like 5.1, 5.11, okay, 5.19, 5.32, okay, here we can have 4.82, here we can have 4.95, 4.98, 5.32. This is random error, okay, this is if this is the voltage. So the error that causes readings to take random like values about mean value is known as random error. These are the effects of uncontrolled variables. Okay, or the variations in the procedure. There might be certain reasons like this. So next, again, what is an error? What is an error? It's the thing which I just said before, that error is equal to uncertainty, it is not equal to the mistake. The mistake is something like an ignorance, carelessness, or environmental conditions are different. Some experiments using one instrument, another experiment using second instrument. For instance, we might be using vernier caliper of one company for taking one reading, then another caliper which is having different types of scale for taking another reading. These are some kind of, I can say these are kind of some kind of carelessness, if not exactly mistakes. So if we are going to work, if we are going to generate data on which we have to apply statistical analysis, it is important that the data is as accurate as possible. So errors is equal to uncertainty that we are working on. Mistakes in calculation or in measurements, as I just said, should always be corrected before calculating the experimental error. So measured value is equal to the mean value plus error. Okay, this mean value is the best estimate of the measurement fx, and delta x is the uncertainty or error in the measurements. So the error can be relative or percent error. We will discuss other types of errors as well. Like we discussed the systematic or random error, we will be mostly working on the random error here only. Systematic error might be due to the faulty calibration, the incorrect calibration or incorrect use of the instrument, change in condition, for instance temperature rise, maybe the change of experimenter, all those things. So random error is due to the statistical variation which we work on. So errors can be represented in these ways: relative error, percent error. The relative error is like I just calculated, is the error per unit mean value. Okay, then percent error is the same relative error into 100. It is error per unit mean value into 100. This is actually percentage. So what we have, we actually do not have the true value. We just know there is some true value, and what we are generating, the data which we are generating is the estimate, of the true value. So that estimate we need to work on. So error has certain properties, the sum or difference. For instance, if there are 3 values for which the error is such as, for x the error is delta x, for y the error is delta y, and for z the error is delta z. So what happens when the final outcome, that is I will put the resultant here, the resultant is equal to x plus y plus z. What do you think? How would the errors behave in this case? This is the property that we need to see, that what could be the maximum error. You know, there is a plus minus sign with delta x, with delta y and delta z. So to see the maximum value, to see the upper bound, the errors are always added, and moreover the absolute values are added. So I can say delta r, or the overall error here, would be equivalent to, I am not putting equal to, it is equivalent to delta x plus delta y plus delta z modulus. Even if the value of r, let me say if the value is 5 plus minus 0.1, 6 plus minus 0.3, it is 7 plus minus 0.4. If these are the values, and the value of r would be, the mean value would be 5 plus 6 plus 7, this equal to 18. Okay, you call it mm, whatever you like to call. Okay, you call it some length. Okay, some temperature. Okay, the temperature we do not had. It is a continuous scale. I'll discuss about the different kinds of scales as well. So, you know, I just kind of made an error or a mistake while calling it a temperature. We never add the temperatures. Temperature is not in a ratio scale, it is in an interval scale. We cannot say that if the temperature of one body is maybe 25 degree, another body is 10 degree, if we keep them together the temperature would be 25 plus 10, it would 35 degrees. So it is not possible. It is in an interval scale, but the length, let me say if it is the height, yes, height if I keep on adding them, yes, that can be added. Okay. So what can be the maximum error? Maximum error here would be 0.1 plus 0.3 plus 0.4, which is equal to 0.8 mm. Please remember this is an upper bound. Okay. So this is delta R. If I need to make it more clear, I can even put it as, I put it equivalent to, put it as equal to plus minus 0.8 mm. So next is product or quotient. What if you multiply or divide the error term? I consider the same values, x plus delta x, y plus delta y, z plus delta z. So the resultant, if it is x into y by z, so here the delta r would be equal to x plus minus delta x or y plus minus delta y over z plus minus delta z. If I talk about the relative error, that is a sum of the relative errors again. So relative error is what? Delta r by r. This is again the sum of the relative errors in a similar fashion like this. I call it equation 1. Okay, this is equation 2. Equation 3 would be delta x by x, delta y by y, delta z by z. Absolute values and sum of these. This is again our upper bound. So what if we multiply the errors with a constant? If result is equal to some constant value a into x, the error of the is the constant times the absolute error. So then the absolute error here is equal to a times delta x. Is it okay? No, when we talk about the errors, errors are absolute terms mostly. So we will put absolute value of the constant here as well, irrespective of its original value. So what if you square or cube or put some degree to a number? For instance, if r is equal to x power n, the relative error is the exponent times the relative error. So this becomes, here we will just take the relative errors only. We are working in a kind of a taking log of this. So we will use delta r by r is equal to n times delta x by x, absolute values. What we need to do, we need to calculate the error and we need to correct the instrument. But this kind of correction that is inculcated to the instrument is known as static correction. Static correction, or If it is just added or subtracted, it is additive in nature, additive. If it is multiplicative, we call it correction factor. This is correction factor. Most of the times, the instruments which we are using are linear in nature, so we will use static correction, not correction factor. Okay, correction factor is multiplied and static correction is added. Added might be, it includes the sign, it might be added or subtracted both. Okay. Next, I will try to take some examples. For instance, if a meter reads a voltmeter, example 1, voltmeter reading is equal to 127.5 volt, and true value is equal to 127.43 volt. So the question is, number 1, what is static error? Number 2, what is static correction? Please remember, static correction is for the instrument. What is the static correction that we should add to the instrument? That should be inculcated every time we use this instrument. So sometimes the static correction or the correction factor is given in the, like in the softwares which are used to calculate the force which is applied during machining. The force is converted into electrical signal, and that electrical signal is into voltage. That voltage is then converted into newtons. There the correction factor is given, that for this range in the software the correction factor is given. Okay, for this range you please apply 1.5, 1.0, whatever the correction factor is. So here it is static correction, because these are additive in nature, we need to find the static correction. So what is the static error? I think it is very easy. So if I take this reading or result as R, okay, the delta R is equal to the reading that is from the instrument, that is the mean value, minus reading that is true value. So this is equal to 127.5 minus 127.43. I will put it 0 and volt. This is equal to 0.07 volt. So this is a positive value, and when we need to add the correction factor is whatever the value comes. So when we need to work on the static correction is subtracted from the mean value, because it is a positive sign, it is subtracted. You can see that voltmeter reading is greater than the true value. So I have put positive sign here. So the static correction, which is denoted by delta C, is equal to minus times delta R, which is equal to minus times plus of 0.07 V is equal to minus 0.07 V. So the static correction value here is minus 0.07 and the static error is plus 0.07. Okay. Whenever the voltmeter is used, this is actually the mean value. This is a mean value from certain number of observations. So we know the true value is there, the mean value is this much. So we took the difference to find the static error, and the static error, the negative of the static error is our static correction. This was example 1. So I'll pick another example. So let me take a temperature. Okay, we consider thermometer reading. Let me say the thermometer reading is 102.66 degrees Fahrenheit, and the static correction is given equal to 0.26 degree Fahrenheit. So we need to find the true value. Okay, so what we have, this is our thermometer reading, which is equal to Rm, this is equal to delta R. So we can find the true value as that is equal to question mark. Now the true value R2 results a true value is equal to Rm minus delta R is equal to 102.66 minus 0.26 is equal to 102.92 degree Fahrenheit. So it can work in either way. So multiple examples can be solved here. So we'll put some questions in the quiz as well. So similar examples can be solved using these relations, and relations for relative errors, relations for absolute errors. Similar examples can be solved. I'll better focus more on the theoretical part in this course. Next is type A and type B uncertainties. So it is important to know what are the type A and type B. The type A uncertainty is the numerical uncertainty that is associated with an input to the computation of a measurement. If it is derived from the calculation based upon the observation data available to the person producing the measurement. So type A uncertainty is due to the experiments which we are conducting, due to the data that is obtained based on certain instruments. If uncertainty is not type A, it is clearly mentioned, it could be type B, which we are not considering, which are not the factors which we are controlling, and we are not working much on type B uncertainty. However, type A uncertainty is important. So if any statistical analysis has to be applied, the uncertainty has to be type A uncertainty. Type A uncertainty may be due to the instrument, again due to the observer, or due to the experimental condition, the way experiments are conducted. So we are working on the type A uncertainties. So most random uncertainties are type A uncertainties. So they vary each time a measurement is made. Type A, they vary, I am putting the characteristics, vary each time the measurement is made. So this uncertainty can be reduced by averaging lots of measurements, but it can never be totally eliminated. So this can be reduced but never can be eliminated. So it can never be eliminated. That is why we use the word confidence intervals, because 100% confidence would never come in random kind of errors. So the type B uncertainties are the uncertainties which are not random, which may or may not repeat each time. So these are sometimes systematic. It is a kind of a systematic error only. So these are systematic uncertainties. So these are actually both the type A and type B uncertainties can be reduced by having a better quality of the instrument. Calibrations can a better calibration can quantify type A uncertainty, and calibration can reduce the level of type B uncertainty as well, but there will always be a small amount of uncertainty that would be left in the instruments. So these are mostly type B uncertainty are mostly systematic, if not always. A few examples here can be like thermal stability. If I pick a specific case, let me say there are many systems, both mechanical and electrical, that can be sensitive to temperature. But for instance, if I pick a strain gauge that depends upon the resistance of the metal foil that makes the gauge, the wire resistance depends upon the temperature. And if a gauge is used in a changing temperature environment, the output caused by the temperature change can wrongly be attributed to changing strain. So the gauge, the strain, the wire, we are talking about the instrument here. So here the effect of large temperature changes can be catered by using certain techniques. The techniques may be temperature compensation, so there will be some residual non-compensated effect. This kind of uncertainty is type A uncertainty. So the examples for the type B uncertainty can be anything that we are not trying to control. Okay, I can put an example for hysteresis. When we load or unload a spring, when we load the spring, when the load is increasing, the hysteresis is something like this. So here actually the load is applied, load applied, I'll put the direction here, it is moving in this direction. Okay, the load is applied and it is increasing like this. Then load, it is load indicated on a scale. This is the load on a scale. It is true applied load. Load applied, actually is applied. So when we unload this, I'll pick another color for you to appreciate in a better way. When we unload this, it becomes something like this. So what happens, this is increasing, this is decreasing, the blue line is decreasing. If I put a line here, mechanical people would appreciate it in a better way. If I put a line here and if I see the values at the true load applied, so a load increasing and decreasing, these values are different. This is for decreasing and this is for increasing. So this kind of error, when the loaded or loading or unloading of spring, when the measurement is taken at this point, this kind of error is type B error. This would always exist. This is not random. This would always exist and it is a kind of a systematic error. So this is an example of spring balance. So type A and type B errors are the classifications. So corrections of systematic effects. When a systematic effect in the measurement process has been identified and quantified, a quantity should be included in the mathematical measurement modeled to correct for it. So let us meet in the next part of this lecture. Thank you.